Good day, everyone. We are from the Department of Statistics of the CUHK. Welcome to this presentation on the topic of derivative of exponential and logarithmic functions. Let's begin with the introduction. Today, we will dive into the fascinating world of exponential and logarithmic functions and their derivatives. These functions are used in many fields, from finance to engineering, and understanding their derivatives is a fundamental concept in calculus. The most common exponential and logarithm functions in calculus course are the natural exponential function, e to the power of x, and the natural logarithm function, ln x. However, we will take a more general approach and look at the general exponential and logarithm function. We are moving on to the derivative of exponential functions. Let's start with the derivative of e to the power of x. The theorem states that let y equals e to the power of x, then y prime equals e to the power of x. The proof is as follows: dy over dx equals limit as h approaches 0 of e to the power of x plus h minus e to the power of x all over h, which equals limit as h approaches 0 of e to the power of x times e to the power of h minus 1 all over h, which equals e to the power of x times limit as h approaches 0 of e to the power of h minus 1 all over h, which equals e to the power of x. It is important to note that the number e can be defined as the base of an exponential function whose tangent line to its graph at the point 0, 1, is of slope 1. Therefore, the value of limit as h approaches 0 of e to the power of h minus 1 all over h is the derivative of y equals e to the power of x at x equals 0, which equals to 1. The result is a beautiful formula that shows the close relationship between e and its derivatives. But that's just the beginning. By applying the chain rule, we can derive a more general formula for the derivative of exponential functions. Specifically, if u is a function of x, then d over dx e to the power of u equals e to the power of u times du over dx in words. The theorem tells us that the derivative of an exponential function is produced by multiplying the function by the derivative of the exponent. Let's look at some examples to see how this works in practice. For example, if y equals e to the power of 17 times, then dy over dx equals 17e to the power of 17 times. Another example is if y equals e to the power of sin x, then y prime equals cos x times e to the power of sin x. Next, let's look at some properties of exponential function f, x, equals b to the power of x. We have studied the derivative of natural exponential function e to the power of x. Now we are revisiting the properties of general exponential function b to the power of x before we investigate its derivative. Here are some properties of exponential function f, x, equals b to the power of x, f, 0, equals 1, meaning the function will always take the value of 1 at x equals 0. F, x, is not equal to 0, meaning an exponential function will never be 0. F, x, is greater than 0, meaning an exponential function is always positive. The previous two properties can be summarized by saying that the range of an exponential function is 0, infinity. The domain of an exponential function is infinity, infinity. In other words, you can plug every x into an exponential function. In addition, if 0 is less than b which is less than 1, then f, x, approaches 0 as x approaches infinity and f, x, approaches infinity as x approaches negative infinity. If b is greater than 1, then f, x, approaches infinity as x approaches infinity and f, x, approaches 0 as x approaches negative infinity. Now let's look at the derivative of exponential functions. The theorem states that let f, x, equals a to the power of x, then f prime of x equals a to the power of x times ln. The proof is as follows: using property of logarithms, we write a equals e to the power of ln, then f, x, equals a to the power of x equals e to the power of ln, to the power of x equals e to the power of ln, x equals e to the power of x times ln. Note that a is a constant and so ln, is also a constant. By differentiating this function by the chain rule, we have f prime of x equals e to the power of x times ln, times ln, equals a to the power of x times ln. Let's look at an example. Let y equals 2 to the power of x find y prime. The solution is as follows: y equals e to the power of x times ln 2, so y prime equals e to the power of x times ln 2 times ln 2 equals ln 2 times 2 to the power of x. It's important not to confuse the two derivatives we have learned so far. The derivative d over dx, x to the power of n, equals n times x to the power of n minus 1, which is known as the power rule. The derivative d over dx, a to the power of x, equals a to the power of x times ln, a, which is known as the derivative of an exponential function. For the power rule, the exponent is a constant and the base is a variable. For an exponential function, the exponent is a variable and the base is a constant. Let's look at another example. Differentiate y equals 5e to the power of x over 3e to the power of x plus 1. By quotient rule, we have y prime equals 5e to the power of 2x plus 5e to the power of x minus 15e to the power of 2x, are all over 3e to the power of x plus 1 squared, which equals 5e to the power of x over 3e to the power of x plus 1 squared. Here, we have an example of real-life application. Suppose that the position of an object is given by s of t equals t times e to the power of t. Does the object ever stop moving? It states that if the object stops moving at a point, the velocity, which is the derivative of the position function, will be 0. The derivative is calculated as s prime of t equals e to the power of t plus t times e to the power of t, which simplifies to 1 plus t times e to the power of t. To determine if the derivative is ever 0, we solve 1 plus t times e to the power of t equals 0. Since exponential functions are never 0, we find that s prime of t equals 0 at t equals -1 only. So, the object will stop moving once at t equals -1. If we disallow negative values of t, then the object will never stop moving. Now let's move on to the derivative of logarithmic functions. Let's start by taking a closer look at the derivative of ln x. The theorem states that if y equals ln x, then y prime equals 1 over x. To understand how this works, we will use implicit differentiation. Recall that e to the power of y equals x. Differentiating both sides with respect to x, we obtain e to the power of y times dy over dx equals 1. Solving for dy over dx, we get 1 over e to the power of y, which is equal to 1 over x. What about the derivative of ln x for x less than 0? Let's consider a special case. If x is less than 0, then the absolute value of x equals -x. By the chain rule, we have d over dx ln -x equals 1 over -x times -1, which equals 1 over x. Hence, we have shown that the following theorem is true: let u be a function of x, then d over dx ln absolute value of u equals 1 over u times du over dx. Now, let's apply what we've learned to some examples. For instance, if y equals ln 7x, then y prime equals 1 over 7x times 7, which equals 1 over x. Another example is if y equals ln x squared, then y prime equals 1 over x squared times 2 times, which equals 2 over x. Alternatively, we can write y as ln x squared equals 2 ln x, so y prime equals 2 times 1 over x, which also equals 2 over x. Moving on, let's now turn our attention to some important properties of logarithmic functions. F x equals log base b of x. It's worth noting that the domain of the logarithmic function is 0, infinity, meaning we cannot plug in 0 or a negative number. The range of the logarithmic function is infinity, infinity. Moreover, we have the following properties: log base b of b equals 1, log base b of 1 equals 0, log base b of b to the power of x equals x, and b to the power of log base b of x equals x. Additionally, we have log base b of xy equals log base b of x plus log base b of y, log base b of x over y equals log base b of x minus log base b of y, log base b of x to the power of r equals r times log base b of x, log base b of x equals ln x over ln b, and log base b of x equals log x over log b. Now, let's delve into the derivative of logarithmic functions. The theorem states that e over dx, log base of x, equals 1 over x times ln. To prove this theorem, we will use the change of base formula. Recall that, log base of x, equals ln, x, over ln. Differentiating both sides with respect to x, we get d over dx, log base of x, equals d over dx, ln, x, over ln. Applying the quotient rule, we obtain 1 over ln, times d over dx, ln, x, minus ln, x, over ln, squared times d over dx, ln. Since d over dx, ln, equals 0, we are left with d over dx, log base of x, equals 1 over x times ln. Note that a is a constant and so ln, is also a constant which is factored out of the derivative. To see how this works in practice, let's look at some further examples. Suppose y equals x to the power of x for x greater than 0. To find y prime, even though y equals x to the power of x does not have a constant base, we proceed to rewrite y as y equals x to the power of x equals e to the power of ln x to the power of x, equals e to the power of x times ln, x. Then, using the chain rule, we get y prime equals e to the power of x times ln, x, times, ln, x, plus 1, which equals x to the power of x times, ln, x, plus 1. Another example is differentiate r, w, equals 4 to the power of w minus 5 log base 9 of w r prime of w equals 4 to the power of w times ln, 4, minus 5 over w times ln, 9. Another example is differentiate f, x, equals 3e to the power of x plus 10x cubed times ln, x f prime of x equals 3e to the power of x plus 30x squared times ln, x, plus 10x cubed times 1 over x, which equals 3e to the power of x plus 30x squared times ln, x, plus 10x squared. That concludes our presentation on the topic of derivative of exponential and logarithmic functions. Thank you for your attention.